Now, today we will start to talk about more Penrose pseudo-inverse. So, let's see what it is. Suppose we have a set of equations which we want to solve with. The system can be written as, we can write it in a matrix form of Ax is equal to B, right? Where A belongs to R n by n, X belongs to R n, and B belongs to R n. So this is the general form. If A is S squared, so A belongs to R n by n, and rank A is equal to n. What does it mean now? Rank n is equal to n, and A is in R n by n. What do we understand from this sentence? Statement. Shimon, what do you understand from this? Sorry?
Rank n means
Rank is n. What does it mean? Rank
the meaning of number of independent rows columns
is n. So what do you understand? What do you understand? A is R n by n and rank is n. We know that rank means number of independent rows or columns. It doesn't matter which one you see, it says it's n.
Full rank.
It's full rank. So what do we understand from here? What is the size?
1 plus 1.
N by n. What is the rank? N. It means that the matrix is non-singular. Why? Because the determinant is not 0. Determinant 0 means that the rank is not n. It should be at least n, at most n minus 1. So, therefore, then we can do this. We can say that Ax is equal to B. We can multiply both sides by A inverse. So X is A inverse B. So this is a very easy situation. We know it from before. This is if A is squared. If A is not a square, in general, A inverse doesn't exist. Well, you will see that this is kind of a lie. It doesn't exist means that we cannot compute, let's say we write it in the correct form, we cannot compute A inverse. And in general, we cannot compute A inverse. Why? Because we know that A inverse is defined if it is a square. However, we can calculate pseudo-inverse. I use the word pseudo-inverse, but we need the more Penrose pseudo-inverse. which is denoted by A plus. A plus. Let's look at our set of simultaneous equations in more details. What I mean, we are in this form. Ax is equal to b. A is Rm by n, so it is not squared. And let's see it in a bit of details. So we have this Ax is equal to b, because I erased it, so I want to write it down. It is Rm by n, and the rest you can guess what the sizes are. So it will be something like in the matrix form A 1n, sorry, 1 1 till A 1n, A m1 till A mn, x1, xn. On purpose, I have shown it smaller so you can see that I mean m is greater than n. b1, bm, and m is greater than n. What do you understand when I say that m is greater than n? First thing that you understand, Kathleen, what do you understand when I say that m is greater than n in this matrix? In here, if I say that m is greater than n, what does it mean? Yes, first observation. We call it number of rows is greater than number of columns. So this is matrix point of view. Now, Suman, from equations, sets of equation point of view, what does it mean? M greater than n.
We have this number of x.
More equations are not.
Sorry?
More equations.
More equations. Number of equations is more than number of unknown. If this is the situation, we call this type of equation today in the MATLAB course I told you. What do we call them? Overdetermined. We have overdetermined situation. Now we will talk about it in details, what we mean by overdetermined and how we can solve it. We understand if it was squared, it was non-singular, we were multiplying by A inverse, and we said that in order to solve it we are using pseudo-inverse. So we continue by saying that in order to solve this equation, we will use as, because A plus A is equal to R. Remember, we are talking about pseudo-inverse, and you see that pseudo-inverse is very general. The normal inverse that you knew up to this stage were actually a very special case of pseudo-inverse. But A inverse is not I. It might be I, but in general it's not I. We will do a numerical example and we see. So we have AX is equal to Y, sorry, is equal to B. Then I have A plus AX, A plus Y. Then I will have X is approximately A, not where is Y come from? Is A plus B. Y approximately, because a bit later today, especially when we finish this chapter and we go to the next chapter, which is even very much important, we will talk about singular value decomposition. You understand that we are estimating A plus Y using least square error. Today, graphically, I will show you what I mean by estimating using this least square error. But because we are estimating, it means that we are estimating our values. But our estimation is a good estimation. This formulation is true if A is also non-singular. Automatically A plus will turn to A inverse, and this roughly equal will become exactly equal. Now, we will go over the derivation of A plus actually again, and then later after next chapter finish towards the end, we will do one detailed numerical process how you can calculate A plus. So we will see how we can derive it. But there are some formula which help us to calculate A plus for some specific situations. In the exam, we will decide, all of us together, if you want to have an open computer exam, which means that you can have your laptop with yourself, which means you might have your math lab with yourself, then we will not calculate, the question will not be that I give you matrix A and I want you to multiply and do some process to get A plus. Because in MATLAB we can write P in and calculate it for you. But if we decide that we will not use our computer, we only use our notes, then those type of questions might be involved. But it is too early to talk about it. In order to calculate A plus, we may use, there is a theorem that under what condition we can use it. We will talk about that theorem also. A plus is equal to A transpose A inverse A transpose. MATLAB uses P-inv. You give the matrix to calculate the pseudo-inverse function, which uses singular value decomposition. Our next chapter to calculate it. I am calculating the pseudo-inverse, and I have the inverse here. We said we are calculating the pseudo-inverse because it is not a square matrix. What can we say about this? Is it a square matrix? A transpose A, is it a square matrix? Okay? Multiply by A transpose. Can you tell me what is the size of A transpose? N by N. They are the same as each other, so the result will be matrix B, which is the what is the size? N by N. So any matrix multiplied by its transpose is definitely a square matrix. We don't know if it's a singular matrix or not, but it will be definitely a square matrix, and in the case that this rectangle, we will get we talk about the non-singular matrix. So this is how we calculate it. This is how we calculate it actually for this numerical example that I want to solve. And after that, we will talk about the theorems that under which condition we can solve or we can calculate A plus by using this. Do you have any question up to now? Do we understand why we need to have this more Penrose pseudo-inverse? Right? So the numerical example is this. Find the solution for x1 plus 3x2 is equal to 17, 5x1 plus 7x2 is equal to 19, 11x1 plus 13x2 is equal to 23. And we know that this sets of equation are linearly independent. Because if they were linearly dependent, it means that we know one of them and we can use two of them. So, what is A? 1, 3, 5, 7, 11, 13. Right? And it's clear that A inverse doesn't work. We have to go for pseudo inverse. So let's calculate the pseudo inverse by using the formula that we have. A transpose A means that we have to calculate 1, 5, 11, 3, 7, 13, multiply by 1, 5, 11, 3, 7, 13. And if you do it, you will get, I have done the math that we got this 2 by 2 matrix, which is 147, 181, 181, and 227. And if you calculate the determinant, it will be 608, which means that it is non-singular. So we can calculate the inverse. A transpose A inverse, by using your calculator, you can easily calculate the 2 by 2 matrix inverse. And if you do it, you will get these numbers. Sorry that I'm cheating from my notebook because I have calculated them. 0.3734 minus 0.2977 minus 0.2977 and 0.2418. So we have calculated the inverse. What is the next step? The next step is I have to multiply it with the transpose of A. So my A plus will be 0.3734 minus 0.2977 minus 0.2977 and 0.2418 multiplied by our inverse, by our transpose, which is 1, 5, 11, 3, 7, 13. And if you do it, you get a plus 2b, a plus 2b, yeah, big matrix of 0.52. Okay, I'm rounding it by 2, so it will be much easier for us to write them down. Minus 0.22 is 0.20. 0.24 and minus 0.13. So this is also a plus. Do something for me. Calculate a plus by a. You will see that it will be I. Not now, we'll do it at home. And if you calculate a plus, you will not get I. Now, if you have a plus a, you will get I2. If you have a plus, if you have a plus, what do we expect to have the size here? Multiply a by a plus. What will be the size? 2 by 2. What is a? A is 3 by 2. What about this one? This is 2 by 3. So you get I3. But if you do it, you say that you will not get I3. So now we continue. We know that Ax is equal to B. So I keep the equations because I need them. So I will have B to be 17, 19, 23. So I will multiply everything by A plus, so my X will be roughly multiplication of minus 0.52, 0.43, minus 0.22, 0.20, 0.24, and minus 0.13, multiplied by RB, which was 17, 19, 23. It is 2 by 3 multiplied by 3 by 1. We will get the result to be 2 by 1, and we get X to be 0 minus 7.51, 0.51, and 8.12. How can I check my answer? How can I check my answers? If put the values into the equation, it has to satisfy it, and I do it. Let's see what will happen. I put minus 7.51 plus 3 multiplied by 8.12. 5 multiplied by minus 7.51 plus 7 multiplied by 8.12. 11 multiplied by minus 7.51 plus 13 multiplied by 8.12. And I get results of 16.84, 19.26, 22.89. So as you see, we don't get exact values. This is approximately 17, this is approximately 19, and this is approximately 23. But the question, what is going on? we said A inverse is actually an approximation. A inverse try to have this least square error. In other words, we want to minimize some error function. It means we are not getting exact value. But what I want to do is this. Let's draw tell me, if I want to draw this equation, can you tell me that what is this equation? This equation of the line, this is the equation of the line, and this is the equation of the line. So let's draw the three equations of, let's draw the three lines, not equation of the lines, three lines. Now, when I have a set of equation and I solve it, what do I find? The intersection point. Now, I have three lines and I solve it, so it means that I have to find the intersection point, whose x is minus 7.51 or y is 8.12. So, let's see what will happen. I have drawn them in MATLAB, so I will try to surprise you by my nice drawing. This is my x-axis, my y-axis, 7.8, let's say, 8, 8.2, 8.4, 8.6, and here my x-axis is minus 8, minus 7.8, minus 7.6, minus 7.4, minus 7.2, minus 7, minus 6.8. Now, first equation with blue. It starts from somewhere like here. So approximately, this is the first equation. Let's have second equation. Let's have it black. So it starts from here and it goes into, let's say, this point. And let's have the next equation in red. And if you draw, and this is the third equation. Well, we have three equations. And we want these three equations to cut at one point. But the reality is that how many points do we have? 3 points. So, and if we draw a line, we will see that it will be somewhere like, I don't know, here. So what it does, it tries to minimize, forgive my back drawing, so you might not feel the concept of least square in here, but it tries to minimize this distance of the point between these three. This is how the pseudo-inverse works. Actually, that's why the system is overdetermined. We cannot find an answer because there isn't any point which is on all the three lines at the same time. So these two lines have one intersection here, these two lines have one intersection here, and these two lines have one intersection here. So pseudo-inverse is an approximation, and that is why we were not you will not be able to find the inverse. Now, it is always good to somehow visualize your answer, or in other words, it's always good to see what you want to minimize. Because least square error is one option, but it's not necessarily a good option. Depends on your application. Sometimes, like in image processing, if you want to do it with, let's say, use column mapping. So there exists lots of other techniques. We don't talk about them in this course, but we could use them. Now, so we have seen up to this point, I wanted to tell you that why we need pseudo-inverse, how it really works. So let's talk about theories that we had about this pseudo-inverse. Several of these theorems already have a proof in our book, which I tell you, and you can go and read those proofs. But mainly we don't want to know the proof. What we want to know is that this theorem exists, so what is the consequence of this theorem? So we try to use the consequence of the theorems. But I will write down all those theorems. Our book has summarized them very well. So consider linear transformation in A, which goes from x to y, which is our subdomain. So we define T to be from, or a complement orthogonal of model space of A, the range of A transpose, not the range of A, where such that T x is equal to A x. So we define a transformation like that. And of course, because we apply T on x, so x belongs to NA, the complement orthogonal of A. We know that T is bijection, bijective. What does it mean bijective? What's the meaning of bijective? What is the meaning of bi? Two. So what are the two properties that it has? What is this? 1 to 1 and onto. In the book, it has proved for us that it is why it is onto, but we know that it is 1 to 1 because NA is equal to 0 definitely. And I have noted in my note that proof of onto. Check the page 24 of our book. But proof is not very important. So T is 1 to 1 and onto. With A and T defined as above expressions. So now we define A plus pseudo-inverse. Can you tell me that what is the domain of A plus and what is the codomain? Knowing all of these ones. Someone? Yes, y to x, because it's inverse from y to x. In a way that This is very, in my opinion, unfriendly way of defining the pseudo-inverse. Pseudo-inverse is not something new. In the Moodle, I will upload the paper which introduced pseudo-inverse. It has been published in 1955. So it's over half a century years old topic, but people are still using it because the consequences are very important. Theory. If A belongs to R n by n and R, the rank R, then G is the pseudo-inverse if and only if. In other words, I can tell you that this matrix is pseudo-inverse of the other matrix that I have if there are four conditions, four principles, P1, P2, P3, and P4 are valid. And let's see what they are. AGA is equal to A. In other words, A plus A should be A. G should be also G. Three and four are very important because they can introduce new things to us. AG transpose, if it is equal to AG, and if GA transpose is equal to GA. So if all these four are true, then we say that we have the pseudo-inverse. Why 3 and 4 are very important? Because if P1, P2, and P3 are valid, but not P4, then we have right inverse. And if P1, P2, P4 are valid, but not P3, so P3 is not valid, but P4 is valid, then guess, what do we have? We have left inverse. You may remember that we talked about right and left inverse in the previous example, in the previous class. Now, let's do an example that how these principles can be used. A numerical example. Consider A is 1 to 2. Verify directly that A plus is equal to 1 over 5 and 2 over 5. How can we verify it? You have to say that this is my G. You have to say that this is true. This is true. This is true. This is true. We know what is A. We know what is G. You just put them and you calculate it. A matrix like 3 minus 1 is just a left inverse of A. I mean, it'll be right to be 100%. As P3 is not satisfied. In other words, if you take this matrix instead of G, you take 3m minus 1. And if you calculate P1, you see that it is true, P2 it is true, P4 it is true, P3 it will fail. Do you want me to verify it or can you do it at home? What you need to do, for example, for P1, you say that we have A multiplied by 1 over 5, 2 over 5, multiplied by 1 over 2. This is equal to, let's multiply these two together, 2 by 1, 1 by 2. So the result is 2 by 2. If I multiply, what do I get? 1 over 5, 2 over 5. 2 over 5, 4 over 5. Then multiply by 1 over 2. And if I do, I will get this one multiplied by this, which is 1 over 5 plus 2 over 5, or 4 over 5. And this one is 4 over 5. So 2 over 5 plus 8 over 5, which will be 5 over 5 and 10 over 5. So condition 1 satisfied. Why? Because A, G, A, or A plus A is A. So you have to do for the rest. So whenever I tell you that for this A or for A plus is calculated by this formula, in order to prove that this formula is really the A plus, you have to check P1, P2, P3, P4. Okay? You remember in the high school or in the calculus or in algebra, you have A inverse is equal to this. How do we prove it? You multiply by A and you get the identity matrix. Here, you have to check all the three conditions. If one or two, one of them fail, it's failed. It's not an inverse at all. But if P3 or P4, one of them fail, we switch the quick into the if it is a right inverse or it's a left inverse. If the P1, P2, P3, P4 all stands, then we have a pseudo inverse. So let's talk about some cool stuff about more Penrose pseudo inverse. And these cool stuff, some of them are theorems, some of them are just some notes. Here. If A is this, then A plus is calculated by limit of delta goes to 0 of A transpose A plus sigma squared I inverse multiplied by A transpose. Or it is one way of calculating A inverse is this. A plus is A transpose A transpose inverse, and A plus is A transpose A inverse A transpose. But number 2 and number 3 we have to be careful about something. This formula is true if A is onto. And this formula is valid if A is 1 to 1. What does it mean that it is onto? It means we have independent. 1 to 1 means we have independent. You complete the sentence. If it is onto, we have independent rows. And when it is 1 to 1, it means we have independent columns. Now, also onto and independent in rows means that we will have right angles. And if it is 1 to 1 and we have independent columns, means that we will have left inverse. We said if A is S squared, if A is S squared and is non-singular, what is A plus? If A is S squared and it is non-singular, it's like a normal matrix. What is A plus?
The normal inverse.
The normal inverse. Okay? So, number 4. For any scalar, can you tell me that what is A inverse as alpha plus? What is an inverse of number 5?
5.
1 over 5.
Oh, yes.
A over 5 to 1 minus 1. So what is for alpha? What is it? 1 over alpha. What about if alpha is 0? So, it is 1 over alpha if alpha is not 0. It will be 0 if alpha is 0. Okay? This is something that we will use it later, especially usually when we are talking about singular value decomposition and we want to come back and calculate A plus. Yes?
That it will be 0 when alpha is 0
Yeah,
or
so you
undefined.
put 1.
Sorry?
Undefined.
No.
When alpha is
This is how we define it.
Okay.
But
Look, if alpha is 0, what is 1 over 0? Undefined. So what does pseudo inverse do it? It says it's 0.
should we put the 1
Why should it be 1?
to have the I of the scalar?
Why do we have? Why should I have 1?
Because if we have like the inverse of 5 is 1 over 5. So we
Yes.
have 1.
No.
So we don't want the 1 there.
No, we don't want, because it will be, in general, it should be infinity, it should be undefined. But we define it 0. I understand what you mean. A plus, you say that A plus, alpha plus alpha should be 1. No, not necessarily. Fine. This is how we define for singular situation, because 0 is singular here, it's undefined. 5 is for any vector we belonging to Rn. V plus is defined as V transpose V inverse V transpose. And it is equal to V transpose over V transpose multiplied by V. If V is not 0, if V is equal to 0, we find 0. So for any vector, remember, when we have a vector, we couldn't define the inverse because in traditional inverse, it should be a matrix, not a vector. And it should be a square matrix. But here we have a vector, and now we try to calculate it. There are 3 more cool pseudo-inverses. Six, 7, 8, 1, 0, 0, 0, 1, 1, 1, 1. 0, 1, 0, 0. 1, 0, 0, 1, the pseudo-inverse is itself. 1, 1, 1, 1, the pseudo-inverse is 1 over 4, 1 over 4, 1 over 4, 1 over 4. 0, 1, 0, 0, the pseudo-inverse is 0, 1, 0, 0. Here we have an interchange. If, for the 6, I'm adding this one. If I have 0, 0, 0, 1, it pseudo-inverses itself. And for number 8, if I have 0, 1, 0, 0, the pseudo-inverse, the location of 1 will be changed. And more generally, if here, for number 6, I have alpha 0, 0, 0, inverse, it will be, what do you think? One over alpha, 0, 0, 0. Theorem. This is actually not a theorem which we need to prove. Now, do you have any question? How is it going with your homework? Because there are 2 theorems, and then we start singular value decomposition to see how we can handle the actual calculation of these pseudo-inverse. Now, but singular value decomposition is even much cooler because we can have lots of other applications of it. I think I'm going to stop now, and we can continue on the next lecture by finishing the pseudo-inverse and continue. We're talking about singular value decomposition. It will be good if we join them, so I can solve one example for you how you can calculate the pseudo-inverse by using the singular value decomposition. Any question? If not, someone you may stop the video.